welcome to the video series on the Tour of Go exercise walkthroughs. Today's video covers the very first exercise, loops and functions, from the basics module inside of the flow control statements chapter. Rather than just showing you my solution directly, I aim to explain all the necessary golang concepts and context for you to leave with a deep understanding of what each and every single line of code really means. This first exercise description is slightly longer. It asks us, given a number x, we want to find a number z for which z squared is most nearly x. In other words, we're trying to find the square root of x. And we'll do this by implementing an algorithm called Newton's method. There is a Wikipedia article linked down here below on all the mathematics and history of the algorithm. But for the purposes of this video, all you really need to know is we start with some initial guess z, and then we repeatedly update z using this formula. The description suggests we go for 10 times, 10 updates, print each z along the way. By this, we iteratively improve and get a good approximation. Finally, the question asks to stop early if between iterations the change in our z is very small. So if the z only changes by some very small amount, we simply stop the algorithm. Let's take a look at the provided starter code. From top to bottom, the first line, declare package main. Every Go program is made up of a collection of packages, and the program entry point is by default defined in the main package inside of the main function. So we're simply declaring the main package with this line. Next, we are calling an import. So we are importing an external package, in this case FMT or FOMT as it's called, from the standard library, which is used for formatting operations such as writing, printing to standard out. We have a function definition indicated by the func keyword called sqrt. It takes in a parameter x of type float64 and it returns a float64. This body is empty, and that's where we'll write our implementation of the algorithm. And then finally, we have the definition of the main function, which neither takes any arguments nor does it return any value. Inside of the body, it prints the return value of sqrt of 2. It's always good practice to run the code and make sure we're at a blank state before implementing our code. So we can click run here, and we actually see that the starting code is not compiling properly. We see proc.go 81 missing return. What's happening here? Well, we didn't install any Go tools, so the program is actually executed on a remote server. It's built there, it's run there, and then the output is just displayed on this little web UI. And apparently it's called prog.go. In line 8, it's missing a return, and that makes total sense as this function here, it defines a return value of float64 and the body is empty. So for now, we can simply return a little 1 here. That should make the compiler happy. And we see a program exited. Okay, so we're compiling. What else can we do here? We have this format button. Go comes with a standard formatter, and we click format. It does all the indentation for us. So what's the first thing we'll do? We'll declare our initial guess z equal to 1. So we'll copy in this statement right here, z colon equal to 1. Colon equal is the short variable operator, which both declares and assigns the value at the same time while inferring the type. So in this case, z is inferred to be of type float64, as we're using this untyped floating point literal. The other option that is provided to us is also a short assignment, uses colon equal, and then uses float64 on an untyped integer of 1. And float64 parentheses, it looks like a function call, but it's actually a compile time operation, which is a type conversion. So we have those two options, and they are essentially equivalent to saying var z float64, and then we could say z equals 1, or we could do it all in one line. So these short assignments are just a fancier way or a shorter way to let the compiler infer the type. And out of these 3 options, the first is the cleanest and most idiomatic, so we'll stick with that. So next, we'll write a loop to iteratively update our z. And in Go, there's only one loop construct, the for loop. So we'll go for I colon equal to 0, I is less than 10, I plus plus, and then braces. The for loop has 3 parts separated by semicolons. The init statement comes first, then the condition expression, and finally the post statement. The init statement is executed exactly once before the first iteration of the loop. And here we're creating a new loop counter variable I and set it to 0. Second, the condition expression is executed at the start of each iteration. The control flow of the loop goes on as long as this condition is true. Once it turns into false, the control flow stops and we exit the loop. Finally, the post statement I++ gets executed at the end of each loop's iteration's body. And here I++ is syntax that comes from C or is inspired by C, and essentially means increment I by 1 and store that new value back into I. Inside of the loop, we will grab this Z update as we want to, in every iteration, improve our Z. This minus equal is a compound assignment operator. Essentially means take whatever is in Z, subtract this right-hand side, and store that new value back into Z. We want to print out our Z. So we'll say fmt funct.println of Z. And finally, we'll just return our Z. When we now run this code, we see that Z is printed 10 times inside of the loop, and actually one final time here at the bottom, as we also have a funct.println statement in main. Now, this is working, and we've actually completed the first part of the algorithm. Yet I would like to improve the formatting of the output a little bit. So let's say iteration, or actually I is equal to I, semicolon, Z is equal to Z. We see I equal to 0, Z equal to 1.5, and we finally see I equal to 9 and some very good approximation. So it's a bit cleaner to track. Now that our basic algorithm is working, I would like to restructure it to use something called a named return. In a named return, we declare the return value inside of the function definition. So what we can do is we say Z float64. Here already in the function definition, we declare Z. So now that Z is declared here, we don't need to redeclare it here. In fact, it would give us a compile time error if we did. We see no new variables on left side of colon equal, line 8. So we simply turn it into an assignment, which now it'll run. And furthermore, since the type is already known of Z, we can just say Z equal to 1. And that runs as well. And now one more thing with named returns is we don't actually need to write the value explicitly here, and we simply write a blank return statement. Technically, it would be possible to remove this Z assignment completely here, and the code still compiles. And why is that? Well, by default, variable declarations in Go get assigned a 0 value, which is type dependent. In case of numeric types like float64 and int, the literal number 0 is assigned. So here Z gets the value of 0. For other types like Boolean, it's false. For string, it's the empty string. But here it would be 0. The only issue is that, unfortunately, Newton's method only works with a non-zero starting guess. Otherwise, the algorithm is undefined. That as an aside, it's always good to think, how can we use the 0 values of variable declarations to make our code cleaner and shorter, more succinct? But in this case, I will need to add back that assignment. And we'll also now add some more code to this function. So it's actually not recommended to use a named return. I just wanted to show it, but it's really meant for very short functions, which only consists of a couple of lines. And this function is getting a little long now. So I'll just go back to the regular function definition with the declaration here inside of the function body, and then the return at the end, the regular return. We're moving on to the final part here. We are tasked to stop the loop condition once the value has stopped changing between loop iterations, or by a very small amount. So we can define a tolerance. What is our tolerance? It's a constant. First of all, it's not a variable. We'll define it once, tolerance float 64, and we'll set it to some very small value like 0.0001. And again, the compiler is smart enough to figure out that this is a float 64 from the untyped literal. Now what we can do is we can see, did the z change more than the tolerance or less than the tolerance? So for that, we'll define a variable previous. We'll set it equal to z just before updating z. I will still print out all of our information here. But now what we'll do is we'll define a diff, which is z minus previous, right? And since z can change in both directions, we're seeing that here. It first increases to 1.5, then it decreases to 1.4. We actually need the absolute value, which we'll get by using math.apps. So we'll import the math package up top. We get the difference, and now we check, is the difference less than our tolerance, right? If this is the case, we want to exit the loop. We want to stop the control flow. We want to return. So what we can do is we break. So if we run this code now, we see that after the fourth iteration, or between iteration 3 and 4, I equal to 2 and I equal to 3, the difference between the z is so small that it's not worth to compute another iteration. One more small note is that if statements in Go, they can use parentheses around the conditions, and it works. It compiles, it runs, but it's not idiomatic Go. It's cleaner to simply omit the parentheses. And in fact, if we were to format the code, we would see that the parentheses are removed. One other thing we could do here is we can move this diff declaration inside of the if statement. So if I just cut that out, paste that in here, separate it with a semicolon. Now if I format, we should see it's added a space here, which is quite nice. So always use format. It's a brilliant tool, part of the Go toolchain. Might look strange if you're coming from a different language to declare this variable as part of the if, but it kind of makes sense as this difference, it's only used here in this condition, right? And we could use it inside of the scope of the if, but outside of this if statement, this diff won't be usable or undefined. And that's it. We're done. We've solved the first exercise on the tour of Go. I know this has been a longer video, but I really wanted to cover all of these fundamental concepts as we went along. And I really hope that you've gotten something out of this video, something valuable. And I'll see you on the next one. Peace.